Thank you.
Thank you. Yes, so I will quickly presenting some very preliminary results from the ECMWF latest ocean CIS reanalysis, which is produced with the ensemble ocean data simulation system. So a little bit, sorry, let me just do one thing. Well, okay, so first of all, it's a summary of what we're using operationally at ECMWF. What we call the Ocean 5 is the current operational system, ocean CIS analysis. It's basically using the NEMO ocean model coupled into CIS model, and then with a 0.25 degree resolution and running with 3D FGAT configurations. This is just a schematic plot showing what it looks like and with driving force, and it's also running with 5 ensemble members and simulating in situ date and the surface sea ice concentration, sea surface height, and the sea surface temperature, for example. So the new system currently still under development, so it's just an indicated timeline I want to show you. And what has been done so far is what we called, we produced a prototype reanalysis called ORAS6, preparation 1. And we will do this in an integrated way, so we will prepare a second preparation. And after that, the real production of the ORAS6 should start in Q1 next year. And it will be produced in 2 streams and covering from 1950 onwards until near real time. And this is a table summarizing the change of the system between our current operational and the one we are already produced in preparation 1 and the final system. And the colored text highlighted change with respect to the operational system. And I know it's a very crowded table. Basically, it's just saying pretty much everything changed. And for example, the forcing is changed to L5 hourly forcing with a new freshwater budget scheme. And the model will go into NEMO 4 with a CIS cube model with a new E=5 configuration. And one of the major change is about the data simulation system. We're going to use the EDA based with a hybrid B configuration. And another change is also about SST. Instead of doing the directly enlarging, now we're doing directly a simulation of SST with the NEMO 1. And a few other things, which I'm not going to all the details for the sake of time. So the only thing I have time to talk about is slightly about the EDA, what we do, and I'm going to show some preliminary result of this one ORAS6. So first of all, the new EDA with a hybrid B configuration that we use. So basically, the covariance formulation in NEMO 1 can be written in a way. So B is the modeled covariance matrix, and the reason we call this the modeled because you can also introduce an EDA based B or as well as a ELF based B. But right now we only use the modeled covariance matrix. It can be written in a way with the formulation like that. Here the KB is just a balance operator. Where the DN is the modeled block diagonal matrix of the variance, where you're using the sigma square to specify the variance. And the CM here is the modeled correlation matrix. Within them, we're using a diffusion operator kappa to specify the spatial correlation. And the way we're constructing that is we're using a hybrid background error standard deviation formulation. So here, the background error standard deviation are formulated in a way using both the modeled standard deviation together with the ensemble-based standard deviation, use this formula, so-called softmax approach. And again, the modeled sigma again comprise 2 components. One is a climatology standard deviation, and also a parameterized standard deviation formulated in a similar softmax approach. And one of the important things to mention is the reason we have to use a hybrid background standard deviation is because now current ensemble spread is not ideal, so we cannot using an entirely ensemble-based spread. Here, W, there are 4 dimension is weighted factors, which specify the relativity weight given to different components of the hybrid. The same approach has been taken for the diffusion tensor. So we have the kappa separated into the modeled kappa and ensemble-based, and then the modeled one are separated into parameterized and the climatology-based one. So that's the main concept. And obviously, we have to testing a lot of different configurations. In the end, we have managed to consolidate the hybrid B configuration. And we get the best performance when we're using a hybrid horizontal diffusion tensor, compromising the parameterized tensor in the tropic and climatological tensor in the exotropics. At the same time, we're using ensemble-based vertical diffusion tensor, which will cycle every data simulation window, and is estimated using ensemble gradient from the previous analysis cycle. So what I'm showing here is the temperature root mean square error change when we're using the so-called hybrid tensor minus the parameterized tensor, which is the one we're using currently in Ocean 5. And the blue color means the reduce of the RMSE error, so which is good. And the red and yellow color means increase of the RMSE error, so which is degradation. Obviously, we have most of the improvement, for example, in the western boundary cavern and the ICC. And in the salinities, overall, is a positive impact, even though there are some degradation in some locations. If you look at the vertical profiles in the global, this is again the temperature root mean square error. Error is in the global domain and in the Atlantic domain. So there are different configuration we tested, and we can see the yellow curve is the so-called this hybrid diffusion and give us the best performance, the least root mean square error averaged in the particularly in the North Atlantic area. And then we look at a little bit larger scale climate signals, for example, the heat content and salt content change. So the plot on the left panel is the ocean heat content in up 300 meters, and it's simply just the internal variability. So it's the trend over the last about 10 years from 2006 to 2016. So the two black line actually is derived from two different objective analyses from based on observation. One is the Cora from the Seaman service, one is the EM4 from the Met Office. So the difference between them give you some kind of uncertainty of how the objective analysis see the ocean heat content change. And it's two, OS5 and OS6 preparation 1. You can see comparing these two lines, OS6 preparation 1 is more consistent with these two objective analysis with uncertainty directly in the later period. If you look at the salt content, it's getting more obviously, in particular because OS5 have a quite rapid drifting of the salt content in the South Ocean, while OS6 preparation 1 is better constrained in this early period. Another major performance change is the SST bias in the Gulf Stream area. We have noticed this kind of bias of OS5 SST in this region for a while. So this dipoles of the positive and negative bias is because we have overshooting of the Gulf Stream. It didn't turn eastward, but keep shooting northward. It has been improved quite a bit in our pilot OIP6 because we have changed a different SST margin scheme here. But it's not until we're using a direct simulation of SST with an ensemble-based vertical diffusion tensor, we can really reduce the bias in this OS6 preparation 1. You can see the bias has been reduced significantly in this area. Another area which we see improvement is about the Dino Cycle. So obviously, if we simply do a nudging scheme, by definition, you're going to, particularly if you're nudging to a daily mean product, then by definition, you will reduce the Dino Cycle. So it is the SST Dino range when we're using the nudging scheme as in Ocean 5 and when we do the direct simulation. You can see the enhancement of the Dino range. If you look at the difference, then the positive value showing how larger the difference they are when we do the Dino range. If you normalize that against the nudging scheme, you can see a global average of 15% of damage is noticed, but in some local area, it could be as large as 100% if using SST direct simulation. As well for the sea ice performance, it's quite a challenge area because we are switching to the sea ice cube model, which is a multi-category sea ice model with melt ponds and many other features, but the LIM2 does not have. So the challenge area including, for example, how do you distribute the increment among the different sea ice category? And how do you apply the sea ice increment in the ice 10-stepping scheme? And as well, you may want to introduce in some kind of balance between the sea ice and ocean state variables. So all these areas, including how you grow the sea ice from the open water, matters the performance when you do the simulation with a sea ice cube model. So what I'm showing here is the bias of the sea ice concentration in OS5 in the winter and the summer season, and what it looks like in the OS preparation 1. So the point here is the bias pattern has changed quite much. But if you just look at the magnitude, then they are more or less comparable now. So there's no severe degradation or something. So we're managing to do, sorry, a quite reasonable job so far, but we are still trying to improve this performance in the future iterations. One last result I want to show is just actually we noticed in a preparation 1 run is we notice in the Meridiana overturning circulation, in particular the AMOC. So what I'm showing here is not AMOC, but the Florida Strait transport, which is a most important component of the AMOC. And you can see in the early period, the OS6 preparation 1 have overestimated the transport by quite a lot. We already know that's issue, and we know this is because the mixed layer depth in the Labrador Sea area when we run the OS6 preparation 1 is overestimated. You can see that's comparing to the nudging and comparing to the OIP6 is overestimated in the Labrador Sea area. And we are still using a mixed layer dependent vertical diffusion tensor, which is making the propagation of SSD increment to a very deep ocean. That is not ideal, and that's causing the AMOC to be over excessive in this area. So we know the issue, and we think we can fix that by introducing either the bias correction or using a better vertical propagation, so the ensemble-based way in this area. So, and that comes to my last slide, summary. So basically, we are working very actively to developing the 6th generation ocean and sea ice ensemble analysis. The major system upgrade, as some of them mentioned, the ensemble-based variational DA with a hybrid B, the new NEMO 4 CS cube model using IF5 forcing, direct simulation SSD, and a simulation of level 3 CIs with CS cube model. A few other components I didn't have time to mention or to show any result. And the first prototype has been produced, and it gives us some kind of quite reasonable performance. The final product will cover from 1915 onwards. And yeah, so the last point is just what I already talked about, the very preliminary evaluation of this preparation 1. That's conclude my talk. Thank you very much.
Thank you, Hal. That was really impressive, a lot of work, and I'm really looking forward to this data set as well. We have a couple questions coming in. The first one, great talk. What do you attribute your positive changes in the ocean heat content?
It's quite hard to disentangle the actual source of our improvement, like the heat content and salt content change, because so many things has changed. So it could be the numerical model improvement, for example, a better mixing in our ocean, or it could be the improved forcing, 5 Nowry forcing, or it could be the new EDA. So sorry, I don't have a concrete answer yet. It will take some time to really disentangle these contributions.
Yeah, it seems like there were a lot of changes all in one version to the next. So yeah, disentangling them is a challenge. From Andrea Storto, thanks a lot, Hal. 2 curiosities. Plans for using atmospheric EDA to run your ocean ensemble, and the diurnal amplitude with direct assimilation resembles the NEMO control model, or 3D VAR has an impact on it if you checked that. So do you plan to use atmospheric EDA to run your ocean ensemble, and whether 3D VAR?
Not, yeah. Thanks for the question. We're not going to use directly atmospheric EDA. to run the ocean ensemble. If you by EDA you mean the specification of the B matrix, then no. But we're going to use a perturbed atmospheric forcing from an ensemble of the forcing to drag the ocean, which will of course contribute to the B specification in the end. And I'm not quite sure that's answered the question. And the second part, Dino amplitude with direct simulation. You can only speed check. Yes, good point. I haven't checked the control run because obviously we have used an hourly forcing, but the one when I compared the slides I showed, they both use an hourly FI forcing. And so it's really simply just showing the impact from switching to direct simulation SSD compared to the margin scheme.
Great. All right, thank you. I don't see any other questions. I'll say thanks to all of the